So this is our official day one of the CAPM, of the Constant Acceleration Particle Model, CAPM. Logic very similar to the constant velocity particle model, but now instead of having constant speed and knowing the physics, the dynamics of what it means to be in a constant speed, we're going to look at a constant acceleration. And for objects to have a constant acceleration, the velocity of the particle is going to be changing. So you're going to be speeding the object up or slowing the object down, which is why I gave you those exercises, different scenarios to help you understand some of the graphical interpretations of speeding up and slowing down, how to interpret that data via graph, via equation if we come to that, and also via motion diagram. So we're going to be getting started in constant acceleration today. So the first thing we want to do is look at some definitions and things that we can measure in this model, very similar to the constant velocity particle model, where we can measure velocity, we can measure speed, we measure time, and we'll be doing the same thing, similar things with the constant acceleration model. So going back over some prefatory matters, some introductory matters with the CAPM. So after we look at the solutions to the homework, we're going to then look at how we can translate the physics language of the CAPM to position time, velocity time, acceleration time graphs, and motion diagrams in the context of the CAPM. So basically, we're going to look at the solutions. We're going to look at the graphs that correspond to speeding up, an object speeding up, an object slowing down, an object doing both. And then we're going to see how we can get velocity graphs from those position time graphs. And then from the velocity graphs, we're going to go to acceleration. So let's see how far we can get with that starting today. Then we'll be looking at the motion worksheet. I posted that up yesterday in the materials section. I want you guys to download that if you haven't already, because I want to talk about that at some point today. Also looking at a video demonstration from last year where we were actually outside of the classroom, like directly in front of the classroom, and we were doing the CAPM lab. And I just got a couple of still shots there because it's only 25 seconds and most of the time the video was blurry. So I captured one instance of it. And then we'll be looking back at the CAPM packet. Okay, so let's take a look at the homework that was due yesterday and talk about those solutions. Okay, 1 second. Let's see here. All right, so let me just go do a new share. Let's see here. All right, everybody see this?
No, we're still on the CAPM
Okay.
section.
Yeah, it's probably about to time me out. Wow. Let's try this here. For any chosen displacement between plus 200 meters and negative 200 meters, in 5 seconds, you are to, 1, create a data table, use any displacement gaps you want to. Your starting and ending points can be anything between plus 200 meters and negative 200 meters. I'm more interested in the correct shape and direction of your graphs. Remember the time interval is 5 seconds. Okay, the second thing that we're going to do is we're going to draw a best fit line or curve, as we can see here, and a motion diagram. So each scenario, each claim, I give you the claim, okay, a car speeding up. In claim A, a car speeding up, increasing position in the east only. That's our claim. Now let's create a scenario, an experiment, if you will, and then have the experimental data be evidence for that claim. And so our evidence in this case was not creating an experiment necessarily, but we had a mock data table, translating the data table into a graph, and then going from the graph to a motion diagram. So situation A, a car speeding up, increasing position in the east only. We did this in class. So our data table, anywhere between 0 and 200, you don't have to stop at 200, but in order to have a car speeding up, the gaps in position must increase. So they cannot be equal. You can't say 0 to 3, 3 to 6, 6 to 9, and so forth. They must be growing quadratically or exponentially in the data table. So Arthur has 0, 0, and he chose his first position to be 3, and the first second, and then he starts to grow his gaps after that. 3 to 10, this could have been like 21, 22, but let that one go. So we want to just make sure that we can reflect an increasing gap for every second. So we go 3 to 10, 10 to 20, as he did in this case, 20 to 33, 33 to 50. So the gaps must be unequal, but getting larger. So this would indicate a situation where the car is speeding up in the eastern direction only, because east is the positive y-axis, west will be the negative y-axis. This is nonlinear data, as he indicates here, because the gaps are increasing unequally. All right, and so this is the shape of the curve here, and a motion diagram should also reflect the gaps, starting off very small, then steadily growing larger and larger. So that accurately depicts the car accelerating. Its speed is actually changing over time, and we're going to take a look at that shortly after the assignment. So this is what we should have here. So if you got something like that and your data table shows an increasing gap, you're good to go. We did this also in class. Situation B, a car slowing down, moving from east to the west. So we're going to cross a barrier, as I say here in the hint. So yesterday we had, so Arthur here is going to start off at 40 centimeters at 0 seconds. And then the object is going to be slowing down. That means that instead of the gaps getting larger, the gaps are going to be getting steadily smaller. So he goes from 40 to 10 here, which is a gap of 30, and then a gap of 20 here, and then 10, and then 5, and then 2, and maybe 1, and then, okay, we come to a complete stop. From east positions to west positions from 0 to 5 seconds. So the shape of your graph should be something like this when you are slowing down from east to west. And the data is obviously nonlinear because we are growing, decreasing in gaps, whereas we were increasing there. And so he depicts the situation by having a motion map going from east to west in this fashion. We start off here at positive 40, and then we cross the barrier at 0, and then the gaps are slowly shrinking. Are there any questions or comments here? Did we anybody not see why that's a slowing down case? Now we are decreasing the gaps. When we decrease the gaps, we slow down. When we increase the gaps, we speed up. The gaps are constant. The gaps are equal. That's a constant speed. So we'll have a best fit line, as we'll see in letters G and H. Okay, so that's all in your notes there. So remember to go back over your notes periodically. You don't have to look at them every day, but keep periodically looking at them. Okay, so that's part B, and then part C, we have a situation where a car slowing down, okay, but increasing position in the east. We did that also in class. So we're in the east domain, number one. We know that we're going to be increasing position, as Arthur has 0 to 105. He could have gone to 200, but again, that's just the range. You don't have to. And slowing down. So we know the situation for slowing down, the gaps are going to be shrinking. We're going to be in the east domain, and we're going to be going anywhere from 0 to 200, plus 200. So Arthur has already satisfied that. 0, 0. It goes from 0 to 40 in 1 second, then 30, and then 20, and then 10, and then 5. Accurate. Okay, so the gaps are shrinking, the position is increasing, and thus the object is slowing down. Slowing down, for good measure, he puts slowing down but increasing position, something we put up there, but definitely you want to keep that in mind. Theta is also nonlinear, of course. And again, we're going from 0 to 105, and the gaps are getting smaller. So we start off large and get smaller, smaller, smaller. So we're going to see how that translates to velocity here soon. But right now we're just in position time graphs, and then we'll go to velocity time and then acceleration time. Okay, so letter D, we have a car speeding up, but increasing position in the east, or in the west. So we're in the western domain. The positions are going to get larger in number, even though the signs are negative. That doesn't mean that these are smaller. These are just larger numbers in the west domain. So that, so that means we're in the west, and we want to be speeding up but increasing position in the west axis. So we start off at 0, 0, anywhere from 0 to negative 200, go to 0, negative 5 in the first second. So that's a gap of 5, then a gap of 10, a gap of 15, 20, 30. So the gaps are going to get larger for speeding up. Again, larger gaps, the object speeds up. Smaller gaps, the object slows down every second. And the positions, the numbers are getting larger. And he has a nice motion diagram here for the west axis, west domain. Very small gap here in the first second, then the gaps slowly get larger. Steadily get larger. Any questions on that? So if you have something to that effect, you're pretty good. A through D, you're on a good foot. So far he is perfect. Okay. So letter E, we have a car slowing down, decreasing position in the west. So we'll stay in the west. The numbers are going to get smaller, and the gaps will also get smaller. So we're decreasing position and decreasing gaps to indicate the object is slowing down. So he starts off at minus 90 in the first second, or in the time 0. And then his gaps start to decrease. It goes from 90 to 50, that's 40, then 20, 10, 5, 3. And eventually it's somewhere in here. It's going to come to a stop. Decreasing gaps, you're slowing down in the west. So the curve is going to look something like this. So all the time when we're going to see in our motion worksheet, when we have a graph that looks like this, that's going to be a situation of slowing down. In this case, we're slowing down in the west. We could be slowing down in the east. There's another situation where we can have a slowdown going from east to west, like we do here, or we can be slowing down. We could be slowing down in the east, but decreasing position, right? So we'll have a graph, we'll have the same graph here, but it'll just be in the west. So it's just different ways of doing things. So we want to keep that in mind. That's letter D. And then we went over, right, and so here's the motion diagram associated with that. That's letter D, we did that. So letter E. So we have a large gap and then we're getting smaller and smaller. Hopefully you're tracking that for the future. Even if you know you didn't get this, I would try to write this down so you'll have it for later. And I'll be giving you back your homework soon, so you can make any changes. Okay, for letter F, we have a car slowing down, moving from west to the east. Much like condition B, E and F are not the same. Okay, so even though E is slowing down in the west, F is slowing down from west to east. So why they're not the same. So at time equals 0, the starting point, we have negative 80 meters in the west, and then the positions, the gaps will start to shrink every second. So we're going from 80 to 40. That's a gap of 40, then 30, and 20, and then 5, and 3. So again, he's depicting slowing down situation from western positions to eastern positions. Obviously, data is nonlinear because the gaps are unequal. They're getting smaller, sometimes they're getting larger, but if it's equal gaps, it's linear data. Slowing down west to east. Motion map associated. Time 0, you start off at minus 80, or position 80 towards the west of 0. Large gap, smaller and smaller and smaller, until eventually you come to a stop. Any questions in the logic of that? Private comments? Okay, so hopefully G and H were easier for you guys because we're just dealing with linear data in this case. So we have a car moving at a constant positive velocity headed from west to the east, so west towards the east. So Arthur's data starts off at time 0 at minus 30 in the west, and then the gaps will be the same. 10, 10, 10, 10, and 10. Linear data, constant positive velocity, very excellent, Arthur. Your slope doesn't change, therefore your velocity doesn't change. It's constant and it's positive. Very good. And his easy looking motion map, we've seen this before, the CVPM and samples in class. The gaps are the same every second, 10, 10. So 10 meters every second is what this depicts. You can even take the slope of that. You're going to get a slope of 10. Physically translated, that's going to be 10 meters per second. And likewise for table H, a car moving at a constant negative velocity headed from east to the west. So we start at plus 20 and we're going towards the west. Negative slope means negative velocity and it's constant. The gaps are the same. So gaps of 10 each time. And slope is negative, so negative velocity. And likewise, his motion map depicts the same thing. The gaps are the same. The gaps are 10 meters every second, but negative this time, negative 10 meters per second, or 10 meters per second to the west. Perfectly done. So Tigran S was asking about the squiggly lines. Are we ever going to see that situation? Well, we see the first example of that in I and J. Now, this is the only place where I took a point off each for Arthur, but other than that, he was most excellent. I'll show what I mean here. So in letter I, we have a car in the east domain, staying east, speeding up, then slowing down. So Arthur reflects that accurately in his data table. So 0, 0, we go to 0 to 10. We're speeding up, the gaps are getting larger. And then he starts to have the gaps get smaller. The gaps are starting to get smaller after 30 meters. So this is perfect. Everything here is perfect. Now, drawing of the graph. So the speeding up case should have had a graph that went like this, the quadratic. Let me see if I can, well, I'll show that on the next screen after this. But this is for slowing down. So it should have been quadratic first, like a growing quadratic curve, and then this guy. So you have an attachment. It's going to be like a, I'll show in a second, but it's going to be like a lopsided S, S on its side or something. So grows first, then does this action. But other than that, it's perfect. Okay. So we grow and then we get smaller. So it's speeding up. Arthur's good here. It's good here. Just missed that one little leg, but it's all good. So grows, speeds up, and then slows down. And likewise here, letter J, a car in the west domain, slowing down and speeding up. So he has the speeding up situation. So let's look at the data table. Starts off at 0, and it can be anywhere from 0 to minus 200 because we're in the west, anywhere between 0 and minus 200. So we go 0 to 10. So we're slowing down. The gap is 10 here in the first second. Then 5, 3, from 15 to 18, and then from 18 to 34, it starts to grow. So there's a speeding up situation. He is accurately depicting that, slowing down, then speeding up. The slowing down situation should have been something like this, the curve that comes down like so, then this guy. So curve and then something like that for speeding up. But other than that, that's why we have a -1 on both of those, but really very minor. Any questions on I and J? And of course, with our motion map, we are going to be slowing down. Gaps are getting smaller, then growing, then we're rising, getting larger. So that's, oh yeah, I forgot to mention, each one of these parts, there's 10 parts, each one of these is 5 points each. Why 5 points each? Because I have 5 pairs here, 1 point each. Then those pairs reflected in a graph, so 5 points for the graph. And then in the motion map, you should also reflect those pairs. So each position for each time. So it's 5, 5, and 5. So 15 times 10, 150. Can people see my comments now, or still not able to see my comments on your paper?
Yeah, I can still.
You can see them?
No, I can't.
Okay. Well, I don't know what that is. So I'll just have to write them in the private comments section here. So figure that out. Can anyone else see my comments? Can no one else see what I write? Because like, as you can see here, if I wanted to add a comment, I have to highlight, and then it does that, but you can't see this at all.
I cannot know.
Okay, that's weird. So, I mean, what's the point of highlighting? Okay, so that's the end on that bit. So let's go to our new share. And all right. So does everybody have their CAPM? I trust that we downloaded it or we have it available in some form.
Yes.
Okay. Well, I mean, who doesn't? Send me a private message. Who does not have their CAPM packet? Because that's going to be part of our notes here. All right. Let me draw mine up here. Okay. Let's get mine going. Okay, can everybody see my constant acceleration model? I think I have to do a new share.
We still only see the notes from earlier.
All right.
Oh, no, we see it. Okay.
Who is calling me? I don't know you. Okay. So let's take a look at some definitions that we can think about within the constant acceleration particle model. So I'm here in my CAMI version. You can download that for yourself if you want, or you can write it on your paper, however you wish to do this. But with acceleration, like the CVPM, what is one physical quantity you think that we can measure or we can talk about with the acceleration model? With the acceleration model.
That's a quantity that we
Position?
can.
Meter.
Yeah. Okay. So like with the constant velocity model, we were able to measure velocity, we were able to measure speed, we were able to measure time. So with the acceleration model, what new quantity can we measure? It's actually in the name.
Acceleration.
Yes, we can measure the new physical quantity that we were going to be looking at is acceleration. And we can write that on here. Best I can do on the screen here. So description of acceleration. So we can just, definition of that is we're going to be changing changing velocity. I'll just do it like this. For change in time. And we can summarize that within an equation, delta V over delta T. So the acceleration A will be change in velocity over change in time. We are going to see throughout time that the slope, we're going to get a velocity time graph, and the slope of that velocity time graph will give us acceleration. Very similar to how the slope of a position time graph gives us velocity. So we're going to just be making another slope from the velocity time graph that will give us acceleration. So the symbol of acceleration, well, it's just A with an arrow to indicate that it is a vector, much like velocity is a vector, displacement's a vector. So we have 3 vectors so far that we'll be talking about. We'll be talking about the displacement vector, velocity vector, acceleration vector. And the units of acceleration are meters per second squared, because this is going to be meters per second, and then when we simplify that, it's going to be meters per second squared. So taking a look at the acceleration model again, what other physical quantity that we can measure? Now just go back to your homework assignment. What's another quantity that we used in our graphs?
Time, seconds.
Yeah, we can also measure time, of course, because we had position time graph, and definitely we can look at time as another physical quantity. It's just, and time. Sure, what? Someone give me a definition. Have you participate there? Well, how would you define time? Anyone?
I don't know. I don't know how to define time.
Don't worry about it. Anyone else? Somebody off the cuff?
The intervals in space in between 2 events.
Okay, so we can say a passage of events. I mean, it doesn't have to be perfect. Cool, just a random description. Okay. Passage of events, moments, that sort of thing. Okay, so the symbol of time, of course, is T, and the typical or base unit is seconds. So going back to our homework as well, we were able to measure displacement, another quantity that appears with the CAPM. And we know that displacement, anybody want to tell me what displacement is? What you remember, what you can look at in your notes?
Total distance traveled.
Nope, not accurate.
Oh,
Let's look at, let's see, Leah, do you have your definition of displacement? You can just rattle it from your notes. Don't have it. Change in speed and direction? No. Displacement has nothing to do with speed. This is how well.
Position with its initial position.
Yes, it's a change of position. It's my basic definition of displacement. We go from one position to the next. And as Ala mentioned, final position minus initial position gives us the quantity of displacement. The definition or description is just a change of position. You got to go back in time on those notes for that. Or read your text, both things. Okay, so the symbol for displacement, as we are familiar with, is delta x. The units are meters. And one last thing that we can, if we're looking at an object speeding up, slowing down, what else can we measure, or what other physical quantity comes to mind? So we can measure displacement, we can measure time, we can calculate an acceleration. Yeah, velocity is definitely pertinent because that's going to be the next quantity that comes from the displacement time graph, from those displacement time graphs that you have for your homework. So velocity is also something that plays a role here. Definition of velocity, description of velocity.
The change in position and time.
Okay, a little bit more accurate. Change in position. Basic change in position per time, over time. I think that's what you were trying to say. So like acceleration here, we have change in velocity per time, but velocity is change in position per time. So we can do the same thing. Change in position divided by change in time, which is delta x over delta t, which is, we should be familiar with that to a degree. Velocity is delta x over delta t. Symbol for velocity is v with an arrow to indicate it's a vector. It has a number and it has a direction. All vectors have numbers and directions. It could be going towards the east, towards the west, north, south, diagonal. And the units, meters per second. So that's what we start off with. I mean, we were actually doing the lab, and I have a bunch of cars in my classroom, like these little gray cars, where students push them, you know, just kind of give them a nice little push, whatever. It doesn't have to be any type of push, just push the cars. And then what we do every second is we track the positions that the car will be at each second. And what we're seeing, what we'll see after that push is that the first second, the gap is very large, and then it steadily gets smaller and smaller to indicate that the object is actually going to be slowing down in this case. So it starts off fast and it gets slower. Or we could, if we were inventive enough, we could start off slow and get faster. But we have not been able to do that. I need like an actual constant acceleration car from Fisher Price or something to depict that. But we were able to actually mimic the situation for the object slowing down, which was very good and helped us to get our experimental data, our evidence, and then we were able to draw conclusions, our reasoning, what you guys have been initially doing so far. Okay, so that's the intro here. So if we were actually doing the lab, we could sketch the setup. We don't have to do that here. We've pretty much answered these things. What can we measure? We already understand that we can measure. What can we measure? What's the first thing, or one thing that we can measure again? Anybody?
Acceleration.
We can measure acceleration, and what way could we measure it? You think, I mean, let's think of a way, how could we measure it? Kind of murky right now, right? You can't really, we don't have a device per se, but we'll be able to measure it graphically for right now. So let's just keep it at this for the moment. Acceleration, we could figure out different ways we could measure it, but we'll get to that. The other quantity that we can measure, of course, we can measure time. This is typical. Use your cell phone or a stopwatch. Okay. And that's what I do. And then instead of displacement, which is something that we have defined up top, instead of measuring displacement per se, we can measure the parts that make up displacement. And do you know what makes up displacement? So displacement is a change of what?
Position.
Yeah, we can always measure position just by putting a meter stick down. And then every second a student calls out, we can put a popsicle stick down or something to mark the position that the car is at that particular moment. And I'll show a video here in a second where students were able to do that. Okay, so position, we can measure that. We'll see using popsicle sticks. your eyes or whatever, you know. But that's what we had available. We could measure the position for every second using popsicle sticks. All right. And then velocity we can also measure. Not directly in the lab, but we can definitely calculate what the velocity will be at each moment. Something that we call instantaneous velocity. But in this class, we won't get into that deeply. But we can totally measure velocity as we defined up top. Okay, so we're going to skip all this stuff for right now. We'll come back to this a little bit later as soon as we have gone over our initial motion worksheet. So I want to make sure that everybody has those notes up top. You can either obviously submit this as a picture or whatever by end of day. Okay, so let me go to our next share. Let's see. Okay, I'm gonna stay here. Okay, so we're here. Got a question. Hello. All right, let me see if I can find it real quick. All right. And it's somewhere in here. Okay. All right, let me look for it. All right, I'm gonna blow this up a little bit. It allows me. Darn it. Darn it. Okay, so I captured it. Okay, so as you can see here, title CAPM lab, you can see the gap down below. So like this was students from last year. I don't know if anybody may know them, like Sebastian, this guy Aaron, and Mark. Anyway, they took physics last year. This was around like October, November of last year. And so we were doing the CAPM lab. Can you guys see this full screen?
All we see is like a shadow.
Okay, let me minimize this. Okay, can we see the video now?
Yes.
Okay, so again, I'm not going to show the beginning of it, but as we can see here, there was like the car reached this point in the first second, and then the second second we got here, and then you see that the gaps are getting smaller and smaller over a 5-second time interval to depict the object slowing down. So again, going back to our assertion that for objects that are slowing down, the gaps are going to get smaller and smaller and until we come to rest. And so that's me recording everything. So they had 2 meter sticks here, and we had the popsicle sticks, second 1, 2, 3, 4, 5. And so they had a pretty ingenious way of doing it. You know, had one guy over here putting popsicle stick down, and another guy over here, and another guy timing. So, you know, being real creative to get data as accurate as you can. Then you put it into your data table, and then from there you can go to your graphs, and then from there your position time graph, and then from there you can get velocity time, acceleration time, and the like. So this was just a part of the CAPM that we did last year and years prior. Okay. Get back to here. So back to the smartboard, you guys can see that, correct?
Yes.
Yes.
All right. So again, we looked at some definitions, things we could measure in the model. Went over the homework there. And so now what I want to start looking at is that motion worksheet right here that I wanted you guys to download. So let's guys grab that or pull that up while I get mine over here. The slope of a position time graph gives us the velocity. We do have more than one slope in this situation. And I will tell you right now that in this particular graph, there are several slopes. We don't care how many that we can get, but we can get a slope at each point. But this is, keep it as simple as we can. There are several slopes in this type of curve. There are several slopes here as well. Okay. Let's mark that for the future. Now, there are several slopes in both of these graphs. There's also something happening with those slopes. We know that there are several. The slopes are actually going from a small value to a large value. In this type of curve here, there are several slopes and they go from small slope to large slope. You don't have to necessarily write it on this worksheet, but you know, get a little dicey. That's where I'm at. So we have defined a few things about this particular graph. The object is speeding up. It's in the east. The gaps are increasing. We see that already from our homework. There are several slopes. And those slopes go from very small to very large. Three things we can glean from that. Over here, the slopes go from large slope to small slope. The opposite. We're slowing down to a stop eventually. Here we're getting faster and faster, and it's just growing towards infinity until an outside force comes in, like your brakes. So let's come back over here to the left. So from small slope to large slope. We know by definition that the slope of a position time graph is the velocity. Since these slopes go from small to large, what do you think the velocities are doing?
Would it be increasing?
They would be going, yes, they would be increasing. They would be going from small velocity to large velocity, because by definition, the slopes here are the velocities. That's why we need to keep this in mind. Got it? We'll be doing that many times. We're translating the abstract slope that we see in math to a physical quantity, the physical velocity. So the small slope that we see here, let me just go back and I want to just do this a little bit more robust. Okay, so if you're taking plain notes, let's say that we have position time graph. We start off with, right? Again, just repeat that definition. The slope, or slopes in our case with the curve, of a position time, abbreviated as xt, is R. Now, we have a graph like this. Curve is like that. We have more than one slope. And briefly, the reason why we have more than one is because at each moment on this curve, we can take a slope and we'll see that those slopes look different. They're going to go from small to large. Like this is going to be a very steep line here, and this is going to be not as steep. But we're not going to get into all of that in this version, this class. But I just wanted you to put that definition down and keep that in mind as we go back to the graph. The slope or slopes of a position time xt graph is or are the velocities, right? If the object is speeding up, as we see in the left graph, the slopes, go from small to large. If the object is slowing down, the slopes go from large to small. Now, small to large slopes equals small to large velocities by definition, as we defined it at the top. Therefore, small slopes, large, small velocities. And you see the transition from your abstract slopes in your math classes to an actual physical reality, which are velocities in this case. Slopes mean velocities only on a position time graph. Small to large slopes, small to large velocities. Large to small slopes means large to small velocities in the context of the position time graph. Let's go back to our worksheet here. So back at the worksheet, motion in a straight line. The object is speeding up. There are many slopes, and the slopes go from small to large. We just defined that small to large slopes mean small to large velocities. Could be a little bit more accurate and say zero slope, because at the very edge here, there's nothing. The slope is zero, but small to large slopes means small to large velocities. So what do you think the picture of this velocity time graph would be? Any guesses? Any confident guesses out there?
Like a situation I'll represent it.
Yes. What graph would it look like? What's the line, or how would we draw the graph in velocity, knowing that definition?
Would it just be a diagonal line from the origin up for the velocity time graph?
We are going to be so this is zero. If this is going from small to large velocities, we can say the smallest we can get is zero, okay? We go from 0 to very large values. So we're going to be increasing our velocity. We're going to go from 0 to a very large value. Another thing to keep in mind that these velocities, as they're growing, they're going to be growing in a positive direction. The thing that we, or better yet, this is all in the eastern domain. We know that these slopes are going to go from small to large. So we're going to have small to large velocities in the east only, because this is east. So small to large. That's how we would draw the line of velocity time. And this is the first introduction of this. We'll be doing several examples. Because right now we've just been in these graphs up top. Oh, we've been speeding up. Okay, draw the curve. All right, you know, it's growing and gaps are getting smaller. But now we need to see the relationship of velocity to position, and then later on, the relationship of acceleration to velocity. And they're all directly related to each other. We'll see that as we do more examples. So this is what is going on from this position time graph to velocity time here. Put time, obviously, minor thing. Take a few seconds to make sure you get the idea of that. If there's any, you know, I'm completely lost. I'm like, well, could you go over that again? And just let me know. So I wanted to start off, you know, by giving you the background definition. Then let's translate these slopes to velocity. And so you need to get comfortable with that. And the question is the y-axis meters per second. Yes, velocity is measured in meters per second. Okay, so we had a question. Okay, like position is meters, velocity, VL, that's meters per second. Excellent. And time second. This might be easier to go from velocity to acceleration. What do you think the graph would look like as we go from velocity to acceleration? Now, keep in mind that acceleration is this guy's slope. Any takers out there? What would the graph look like? What kind of slope is this? Is it changing? Is it constant?
It's a constant slope.
It is, in fact, a constant slope. And definition as with velocity is that we know that the slope of a velocity time graph gives us acceleration. This slope is constant. Since this is a constant slope, constant acceleration. What would the graph look like in acceleration then? Since acceleration is constant.
Would it just look similar to the velocity graph?
Not similar.
Where it's increasing?
No, we have a constant slope. So this constant slope means constant acceleration. How would we show constant acceleration down here? The acceleration doesn't change. It doesn't increase or decrease. How would we show that? Let's say that we have an acceleration, just put a dot line there. How would we show this is the same for all time?
Just a horizontal line.
Horizontal line.
It would be a horizontal straight line, yes. Because this would show that the acceleration doesn't change forever. It's constant. Let's say that that's 2 meters per second squared. It's going to stay that way to infinity. because let me go back here. Now again, we're going to go over this again and again and again until we're really comfortable. Take a few days with it. Necessary. All right, so now we just saw earlier XT graph, the position time graph now. Keep things tight over here. For a velocity time graph, let's say we have a VT, we have VT action doing this, and we want to go to AT, acceleration. Slope of a velocity time graph is the acceleration. Sorry about that. Why do we even throw that definition out there? What's the point? How do we get here? Is it just something you feel? Absolutely not. Let's go back to definition of velocity for a second, right? Velocity by an equation is delta x over delta t. This is completely similar to your slope equation in algebra. Slope, change in y over change in x. For many people, this makes it very comfortable. We know we can just throw in numbers and take slopes all darn day without knowing what they mean or translating them. Well, a translation of this slope equation is velocity. Every time you see a division, that's a slope. Every time. Because it's derivative of this idea. You get that? Do you see that?
Yes.
This is why we say what we say. This is slope. This is velocity, delta x over delta t. Therefore, we can say by the logic here that the slope of a position time graph is the velocity, much like the slope of a velocity time graph is the acceleration, because that's also a slope equation. This is a slope equation. What else is slope equation? All of these divisions are slopes. This is the slope of these two guys. This is the slope of this, force and mass. This is the slope of velocity time, et cetera, et cetera. They're all slopes. This is why we say what we say with accuracy, with confidence. And then once we know what the slopes are of a velocity time graph, we can then make the acceleration graph. Is there a slope of an acceleration? In our context, there is not. We stop at acceleration. In physical reality, there can be slopes of acceleration, but the time intervals are so small that we don't worry about them. So it's a concept called jump. You ever been on a bus or a train, that first second, that lurch, if you're standing up or sitting down even, you feel that instant jump? Well, that's acceleration change. But it doesn't happen all the time consistently. So we'll leave it at that. The homework, we should turn that in. We'll continue with this tomorrow. Friday. Your next quiz, as we wrap things up, will be next Tuesday. All right. This week, nothing at all. So I'll have a slot for these notes to be uploaded, and that's it.